The assertion that the National Electrical Code places a limitation of 100 feet on conduit runs between electrical boxes is inaccurate. The NEC itself does not impose any restrictions on the distance separating electrical boxes within a conduit system. However, it is crucial to understand that the NEC serves as a foundational standard, and local jurisdictions possess the authority to adopt and enforce their own supplemental codes and amendments. These local modifications can, and often do, introduce regulations that are more stringent or specific than those outlined in the NEC. Therefore, the presence of a 100-foot limitation on conduit runs would be a matter of local code adoption, not a provision within the NEC itself. To definitively determine whether such a restriction exists, one must consult the local building department or electrical inspector responsible for the jurisdiction in question. They will possess the most current and accurate information regarding local code requirements. The NEC, published by the National Fire Protection Association, undergoes revisions every 3 years, ensuring that the code reflects the latest advancements in electrical safety and technology. It provides comprehensive guidelines for electrical installations, covering a wide range of topics including wiring methods, overcurrent protection, grounding, and equipment installation. While the NEC aims to standardize electrical practices nationwide, it recognizes the need for local authorities to address specific regional concerns or adapt to unique environmental conditions. This flexibility allows jurisdictions to tailor their electrical codes to suit their particular needs. When designing or installing electrical systems, it is imperative to adhere to both the NEC and any applicable local codes. Failure to comply with these regulations can result in failed inspections, costly rework, and potential safety hazards. To ensure compliance, it is recommended to consult with a licensed electrical contractor or engineer who is familiar with the local code requirements. They can provide guidance on proper wiring methods, conduit sizing, and other critical aspects of electrical installations. In the context of conduit runs, factors such as the type of conduit, the number of conductors, and the ambient temperature can influence the allowable distance between support points. The NEC provides tables and guidelines for determining the appropriate support spacing for various types of conduit. These requirements are intended to prevent excessive sagging or deflection of the conduit, which can damage conductors or create safety hazards. While the NEC does not explicitly limit the overall length of a conduit run, it does address voltage drop considerations. Voltage drop refers to the reduction in voltage that occurs as electricity travels through a conductor. Excessive voltage drop can impair the performance of electrical equipment and reduce its efficiency. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to select conductors of adequate size and to keep conduit runs as short as possible. In situations where long conduit runs are unavoidable, it may be necessary to increase the conductor size or to install voltage drop compensation equipment. In addition to voltage drop, conduit fill is another important consideration. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. The NEC limits conduit fill to prevent overheating and to facilitate the pulling of conductors. The allowable conduit fill percentage varies depending on the type of conduit and the number of conductors. When calculating conduit fill, it is important to include all conductors, including grounding conductors. The NEC provides tables and guidelines for determining the appropriate conduit size based on the number and size of conductors. Proper conduit sizing is essential for ensuring the safety and reliability of electrical systems. In summary, while the NEC does not impose a specific length limitation on conduit runs between electrical boxes, it is crucial to be aware of and comply with any applicable local codes. Additionally, factors such as voltage drop, conduit fill, and support spacing must be carefully considered to ensure the safety and performance of electrical installations. Consulting with a qualified electrical professional is recommended to ensure compliance with all relevant codes and standards. Furthermore, it's vital to differentiate between different types of conduits, as their applications and installation requirements vary. Firstly, rigid metal conduit, or RMC, is a heavy-duty, threaded conduit generally made from steel or aluminum. It offers excellent protection against physical damage and is suitable for both exposed and concealed locations and for direct burial. Secondly, intermediate metal conduit or IMC is a thinner-walled version of RMC, making it lighter and easier to work with. It provides good protection and is also suitable for various applications, often used in commercial and industrial settings. Thirdly, electrical metallic tubing or EMT is a lightweight, non-threaded conduit commonly referred to as thin-wall conduit. It is primarily used in concealed locations and offers good protection for conductors. EMT is easy to bend and cut, making it a popular choice for general wiring. Fourthly, flexible metal conduit or FMC is a spiral wound, flexible conduit used for connecting electrical boxes and equipment where flexibility is required. It's not suitable for direct burial or wet locations unless specifically listed for those applications. Fifthly, liquid-tight flexible metal conduit or LFMC is a flexible metal conduit covered with a liquid-tight plastic coating. It's used in wet locations or where flexibility is needed and protection from liquids is required. Sixthly, rigid polyvinyl chloride conduit or PVC is a non-metallic conduit made from PVC plastic. It's lightweight, corrosion-resistant, and suitable for direct burial and wet locations. PVC conduit is commonly used in underground applications and for corrosive environments. Seventhly, electrical non-metallic tubing or ENT is a flexible, non-metallic conduit often referred to as Smurf tube due to its blue color. It's primarily used in concealed locations such as within walls and ceilings and is suitable for dry environments. Each of these conduit types has specific installation requirements and limitations outlined in the NEC. The choice of conduit depends on the specific application, environmental conditions, and local code requirements. It is crucial to select the appropriate conduit type and install it according to the manufacturer's instructions and the NEC to ensure a safe and reliable electrical system. The NEC provides detailed information on the allowable uses, installation methods, and support requirements for each type of conduit. When installing conduits, proper bending techniques are essential to avoid damaging the conduit or reducing its inside diameter. Bends should be made with a conduit bender that is designed for the specific type and size of conduit. The NEC specifies the minimum bending radius for different types of conduit to prevent kinking or flattening. When pulling conductors through conduits, it is important to use a pulling lubricant to reduce friction and prevent damage to the conductors. The NEC also specifies the maximum pulling force that can be applied to conductors based on their size and insulation type. Overloading conductors can damage their insulation and create safety hazards. In addition to conduit and conductors, electrical boxes are an integral part of any electrical wiring system. Electrical boxes provide a safe and convenient location for terminating and splicing conductors, as well as for mounting electrical devices such as switches and receptacles. The NEC specifies the minimum size of electrical boxes based on the number and size of conductors and devices they contain. Proper box fill calculations are essential to prevent overcrowding and to ensure that conductors are not subjected to excessive stress or strain. Electrical boxes must be securely mounted and properly grounded to ensure electrical safety. The NEC provides detailed requirements for grounding electrical boxes and equipment. Grounding helps to protect against electrical shock and to prevent the buildup of static electricity. In summary, designing and installing electrical systems requires a thorough understanding of the NEC, local codes, and best practices. Consulting with a qualified electrical professional is recommended to ensure that all electrical work is performed safely and in compliance with applicable regulations. Failure to comply with electrical codes can result in serious consequences, including electrical fires, injuries, and property damage. Therefore, it is essential to prioritize electrical safety and to follow all applicable codes and standards when working with electricity. It is also important to understand the concept of dirtying conductors when multiple current-carrying conductors are installed in a single conduit. The NEC requires that the ampacity of conductors be dirtied when the number of current-carrying conductors in a conduit exceeds 3. This derriting is necessary to prevent overheating of the conductors due to the combined heat generated by multiple conductors in close proximity. The derriting factors vary depending on the number of conductors and the ambient temperature. The NEC provides tables that specify the derriting factors for different conditions. When derriting conductors, it is important to use the correct ampacity rating for the conductor based on its temperature rating. Conductors are typically rated for 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius. The ampacity rating of a conductor decreases as its temperature rating increases. Therefore, it is important to select conductors with an appropriate temperature rating for the application. In addition to derriting for the number of conductors, derriting may also be required for ambient temperature. The NEC requires that the ampacity of conductors be derrited when the ambient temperature exceeds 30 degrees Celsius. This derriting is necessary to prevent overheating of the conductors due to the increased ambient temperature. The derriting factors for ambient temperature vary depending on the conductor's temperature rating and the ambient temperature. The NEC provides tables that specify the derriting factors for different conditions. When derriting for ambient temperature, it is important to consider the actual ambient temperature in the area where the conductors are installed. The ambient temperature can vary depending on the location and the time of year. Therefore, it is important to use accurate temperature data when derriting conductors. In addition to conduit fill and conductor derriting, it is also important to consider the voltage drop in electrical circuits. Voltage drop is the reduction in voltage that occurs as electricity travels through a conductor. Excessive voltage drop can cause electrical equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop be limited to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to use conductors of adequate size and to keep circuit lengths as short as possible. The NEC provides formulas and tables that can be used to calculate voltage drop. When calculating voltage drop, it is important to consider the conductor's resistance, the circuit's current, and the circuit's length. The resistance of a conductor depends on its material size and temperature. The current in a circuit depends on the load connected to the circuit. The length of a circuit is the distance from the power source to the load. In situations where long circuit lengths are unavoidable, it may be necessary to increase the conductor size or to use a higher voltage to minimize voltage drop. Using a higher voltage reduces the current required to deliver the same amount of power, which in turn reduces the voltage drop. In summary, designing and installing electrical systems requires careful consideration of conduit fill, conductor derriting, and voltage drop. These factors can significantly impact the safety and performance of electrical systems. Consulting with a qualified electrical professional is recommended to ensure that all electrical work is performed safely and in compliance with applicable regulations. Remember to always consult the latest edition of the NEC and any applicable local codes for the most up-to-date requirements. Electrical codes are constantly evolving to reflect advancements in technology and to address emerging safety concerns. Staying informed about these changes is essential for ensuring the safety and reliability of electrical systems. Furthermore, proper grounding and bonding are critical components of a safe electrical system. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protective devices to trip and to energize the circuit. Bonding connects all metallic parts of the electrical system together, creating a low impedance path for fault current. The NEC provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to minimize the risk of electrical shock and to prevent the buildup of static electricity. Grounding electrodes, such as ground rods or metal water pipes, are used to connect the electrical system to the earth. The size and type of grounding electrode depend on the size of the electrical system and the soil conditions. Bonding jumpers are used to connect metallic parts of the electrical system together, such as conduit, electrical boxes, and equipment enclosures. The size of the bonding jumper depends on the size of the circuit conductors. Proper grounding and bonding are essential for ensuring the safety of people and equipment. Failure to properly ground and bond an electrical system can result in serious consequences, including electrical shock, fires, and equipment damage. Therefore, it is essential to follow all applicable codes and standards when grounding and bonding electrical systems. In addition to grounding and bonding, overcurrent protection is another critical component of a safe electrical system. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds its rated capacity. Short circuits occur when there is a low resistance path between two conductors. Overcurrent protective devices are designed to trip and de-energize the circuit when an overload or short circuit occurs. The NEC provides detailed requirements for selecting and installing overcurrent protective devices. These requirements are designed to ensure that overcurrent protective devices are properly sized and coordinated to protect electrical circuits from damage. Circuit breakers are automatic switches that trip and de-energize the circuit when an overload or short circuit occurs. Fuses are one-time devices that melt and open the circuit when an overload or short circuit occurs. The choice between circuit breakers and fuses depends on the application and the preference of the designer. In general, circuit breakers are more convenient because they can be reset after they trip. Fuses must be replaced after they blow. However, fuses are often more reliable than circuit breakers and can provide better protection against high fault currents. Proper overcurrent protection is essential for ensuring the safety of people and equipment. Failure to properly protect electrical circuits from overloads and short circuits can result in serious consequences, including electrical fires, injuries, and equipment damage. Therefore, it is essential to follow all applicable codes and standards when selecting and installing overcurrent protective devices. The NEC provides extensive information on wiring methods, which are the techniques and materials used to install electrical conductors. Different wiring methods are suitable for different applications and environments. Some common wiring methods include rigid metal conduit, electrical metallic tubing, flexible metal conduit, and non-metallic cable. Rigid metal conduit, or RMC, provides excellent protection for conductors and is suitable for both exposed and concealed locations. Electrical metallic tubing, or EMT, is a lightweight conduit that is easy to install and is suitable for concealed locations. Flexible metal conduit, or FMC, is a flexible conduit that is used to connect electrical boxes and equipment where flexibility is needed. Non-metallic cable, or NM cable, is a flexible cable that is used for wiring branch circuits in residential buildings. The NEC provides detailed requirements for installing each type of wiring method. These requirements are designed to ensure that conductors are properly protected and that the electrical system is safe and reliable. When selecting a wiring method, it is important to consider the environment in which the wiring will be installed. For example, rigid metal conduit is a good choice for wet or corrosive environments, while non-metallic cable is a good choice for dry, indoor environments. It is also important to consider the ampacity of the conductors when selecting a wiring method. A wiring method must be able to safely carry the current that will flow through the conductors. In addition to wiring methods, the NEC also provides requirements for installing electrical equipment. Electrical equipment includes items such as switches, receptacles, lighting fixtures, and appliances. The NEC requires that electrical equipment be installed in accordance with the manufacturer's instructions and that it be properly grounded and bonded. Electrical equipment must also be suitable for the environment in which it will be installed. For example, electrical equipment that is installed in a wet location must be listed for wet locations. Proper installation of electrical equipment is essential for ensuring the safety of people and equipment. Failure to properly install electrical equipment can result in serious consequences, including electrical shock, fires, and equipment damage. Therefore, it is essential to follow all applicable codes and standards when installing electrical equipment. The NEC is a comprehensive document that covers a wide range of electrical topics. It is essential for anyone who works with electricity to have a thorough understanding of the NEC. The NEC is updated every 3 years, so it is important to stay up to date on the latest changes. There are many resources available to help people learn about the NEC. These resources include books, websites, and training courses. It is also helpful to consult with a qualified electrical professional when you have questions about the NEC. Remember that electrical work can be dangerous. It is important to take all necessary precautions to protect yourself from electrical shock. Always turn off the power before working on electrical circuits. Use insulated tools and wear appropriate personal protective equipment. If you are not comfortable working with electricity, it is best to hire a qualified electrical professional.